when you switch on your video, the video shows you up to your bust. It shows you from your chest to the head, and that is sufficient for a video class and a video conference. It doesn't mean that you don't have the full body which exists in the world coordinate, but in the camera coordinate you are clipped to the most prominent regions from where your expressions, your voice and things are much more comprehensively shown. Of course, if you would like to see actions, then I will zoom out and the whole body will be then displayed. If for a normal talk or any other thing, normally a bust is what is selected. So what effectively in graphic means that your the object is yourself, and that is clipped from your chest to the top, that is head, and that creates a bust image of yourself, and this bust image becomes your viewing window. So similarly, I have got polygons. Polygons will need to create you need to clip these polygons. The world a lot of objects may exist in the world, but a portion of the world is seen through the camera or the viewing screen, so you need to clip it. Why do I need to clip it? Because I don't want to uselessly color or shade or render the whole world, because the only thing that will be visible is which will be the screen, so I don't need to buffer the remaining part of the world. So the idea is just to reduce on the buffering time and the computation and coloring. You need to clip the polygons. So effectively what we have seen is that we have seen in the previous lecture how to clip polygons. Of course, I would like you to go through my videos and look into it. So now today we are going to see line clipping algorithms. Now polygon essentially is made out of vertices, and vertices are connected by edges, and effectively when I say that I'm clipping a polygon, actually I'm clipping edges. So let us see how efficiently I should be able to clip the edges. In the polygons, what we have seen is that we need to check the polygon from each side of the window, assuming my window is a rectangular window through which I'm looking at the world. So it is going to see each edge, say the right edge of the window. If it is clipping, if part of the polygon is being in the scene and part outside, so it needs to be clipped, or the bottom edge of the window, or the left edge of the window, or the top edge of the window needs to be checked. So what you need to check is that you need to check for all the four edges of the window on and clip the polygon. So let us see efficiently, can we decide that okay, this part of the polygon I will only require the right edge to clip, and this part of the polygon I would require the left edge to clip, and so on and so forth. The bottom edge would be for some part of the polygon, and the top edge will be for some other part of the polygon. Effectively, it would mean that I would like to separate out the edges. These edges should be sent so that you do the required calculations with the right edge of the window. The other edges to be sent for required calculation with the bottom edge. Some others will be sent to the left edge, and some will be sent to the top edge of the window, and some which are not going to which are inside the window should not change, should remain the same. So, and the ones which will be totally outside should be totally rejected. So I have these different conditions, but I should efficiently change between these different conditions and work out the process. What we are going to see is that how do I clip these edges from different sides. Okay, so now when we have already seen about the polygon in general, now let us see for line clipping algorithm. So here what you see is that I have got different lines. You see the lines are ending with different points. You see here that I have got point P1 and P2. These 2 points are independent points, but P3 and P4 are connected by a line. P7 and P8 are connected, and of course P7 is on the left side and the P8 is on the right side. There it is going across my window, and I have got P5 and P6 which is within the window, and I should not need to clip that portion. And I have got P9 and P10. It is cutting the bottom edge of the window, and it needs to be clipped. So the idea is that how do I determine it? So here I see P1 will remain, and P2 being outside the window should not be visible. So what you would do is that as per what we learned for polygon, you will check for each edge. You check for the right edge, then for the bottom edge, then for the other two edges, and you get the final resultant clipped image. Now what you have done is that for every point I did a check for all the four sides, and based on these four sides I made a decision that these points or these edges, these vertices and these edges are within the window. And for instance, this line where both the points are outside the window, but it is cutting through the window. So I will find the two new vertices, which will be the edges of the window, the left edge and the right edge, which will connect, which will be part of this segment, which was, or the edge which was there earlier. Now, uh, So, for the image below, consider which lines and points should be kept and which ones should be clipped. So, clipping, we have been assuming that all primitives, lines, triangles, polygons lie entirely within the viewport. In general, this assumption will not hold. So here I have got a case where I have got a line that passes through the right edge of the window, and therefore I need to calculate, and of course this is another edge where you see again both the endpoints are outside, but it is passing through the corner. So basically it needs, this vertex needs to be clipped by both the sides, that is the bottom edge and the left edge, while the first edge needed to be clipped only by the left edge. So what you see is that in some cases I need to clip by a single edge, and in some cases it needs to be clipped by two edges, and it is possible that it may be required to clip by three edges. If we have a possibility, we have to see that. So how do I determine this a particular line with a number x and y, or x, y, and z if it is in 3 dimension for P1, and x, y, z for P2? Looking at these vertices, how do I really make out which edge should I use? The equation of which edge? Edge is nothing else but another line. So basically I'm trying to find out the intersection of the two lines. That is the point where it will get clipped. But how do I choose the edge of the window for which we will require to clip? So since we cannot do, we will try to do it with all four sides, and we will see that we will only succeed with one. So it's a waste of computational time. So how do I intelligently in my algorithm send that particular edge to a particular clipping algorithm? That is, Either it gets clipped by the right edge or the left edge or bottom edge or top edge, or it gets clipped by a double edge, like for instance the bottom and the left edge in the case of the second line which has been displayed. So here I have got a third edge, and I know that this edge need not be clipped, it just need to be rejected, but since there is not a single portion of this line which enters the window, so you need to totally ignore it. But how do I know that it needs to be ignored? So analytically calculating the portions of the primitives within the viewport, you can calculate this, and after you calculate it, you could clip it. So why clip? So the main reason is it's a bad idea to rasterize outside the frame buffer bounds. Basically, you're doing excess computation, and this excess computation is not going to help you in your calculation. So also don't waste time in scan converting a pixel outside the window, because it is not going to be displayed. So what you need to do for point clipping, so given an XP, YP and ZP, check the following. XP, YP, ZP is let it be one of the end point of my edge. So here you see the window having a range. This window range is from WX min to WX max, WY min to WY max, and WZ min to WZ max. Now I've considered this in 3D, but if I would like to consider it in 2D, I don't need to bother about the Z coordinate. Generally, we will do it in 2D because this is done after perspective projection is made, and you need to clip the object. So you need to find out if that particular point, that is XP, YP, ZP, is within these limits. If it is within these limits, you can say that it is in my viewing cube. Now, wait a minute. This viewing cube is an orthonormal cube, but if I consider perspective views like a normal camera, what we see is that it is possible that in foreground objects there is a lesser number of smaller distance of objects are viewed, but as objects go close to the background or far away, more objects are visible within the same window. So the window, instead of becoming being a cube, the clipping could be a form which is shown on the right hand side, which is some sort of a trapezoidal, where you have these. This is my front window, and the gray one is my back window in the Z direction. So what you have is that these lines are actually emanating from a single point into the four with the four sides of the front window, which tells me that the volume or the increases as Z, or the depth axis increases, the area which needs to be visible will be more. Please note that the angle remains the same. The angle that you're seeing here, you're not actually observing a fixed distance, but you're observing an angle that your eye makes with the right edge, left edge, top edge, and bottom edge. So this is any object within this angle will be visible in my viewpoint. Of course, I have got a Z max where I will not show things which are further than a particular Z value. So, but this is in 3D. But the same thing when it's done in perspective projection, this effect of the trapezoidal will automatically get projected onto a 2D screen, and there you don't need to think about a trapezoidal clipping. You can just clip it with a normal square, as in the first case. Here it is the cube, and the cube will reduce to a square, this will reduce to a square, and this perspective projection will also reduce to a square. So now here I have got these points, and if I would like to clip the points, it's very easy. So I need to check if the points are inside this range. So I need to make this check if x is within this range and y is within this range, then we will keep the point, otherwise we will reject the point. Please note, this is an AND, logical AND condition. Both the conditions need to be met for the points to be retained within the window. So what you see here is that these point P7, P4, P10, P2 and P8 should be clipped. Okay, and the points like P1, P5 and P9, the points within the window will not be clipped. Please note here, P8 also needs to be clipped. So here are different conditions, line clipping conditions. Harder examined and endpoints of each line to see if these are in the window or not. So let us check for different situation. Both endpoints inside the window. If both endpoints are within the window, there is no possibility that the edge joining these endpoints or these vertices will cross the window. So I don't need to clip them. They will just be retained. These vertices defining these edges will be retained. The endpoints of these vertices will be retained. Now is that one endpoint is inside the window and one is outside. You must clip it. Now this could be related to the thing being clipped by the right edge, bottom edge, top edge or the left edge. Here we have shown three lines. One is being clipped, needs to be clipped by the right edge, one with the bottom edge and another with the top edge. So we need to clip it. But now these three edges or these three lines, which edge should I run it? I see that all these three lines do not need to be clipped by the left edge, but we do not know it. So we will be actually trying to clip it with the left edge also. We will not succeed it, and therefore we'll say that no, this edge is not crossing the boundaries of the left edge of the window. If it's crossing, it is crossing the boundaries of other three boundaries of the window. So here this problem or this error will exist. Now if both ends are outside the window, I don't know, because here you see that I have put three cases. In three cases, I know one case is totally outside the window, as this case you see here is totally outside, but the other two cases, both though the end points are outside the window, it is actually cutting through the window and therefore it needs to be clipped. Now it is very difficult to know which edge is going to clip, and therefore these are cases where I need to run it for all the four sides and try to solve it. But if I could reduce the second option into just one-sided clipping, and the first option where I just don't take the clipped lines, I just copy them without doing the intersection calculation, I would have reduced it by 1/3. And one thing that I am not taking into account is that I know that a particular line is outside, or there is some mechanism through which I can know that the line is outside the window, I need to summarily reject the line and not go further in trying to compute the intersection of this line with the window. So then I have four conditions. So effectively, I will reduce my edges or lines into either of the four category. So what you see is that when I can reduce it into either of the four category, I would have reduced the number of computation for each conditions. Otherwise I need to do all the four things, the same computation for all the four groups, which is going to take a lot of computational time. So here I've circled that I don't know. It is difficult to know which edge, and therefore one has to do it with multiple edges. So what is a brute force line clipping algorithm? The brute force line clipping can be performed as follows. Don't clip lines with both endpoints within the window. For lines with one endpoint inside the window and one endpoint outside, calculate the intersection point using the equation of the line and clip from the point out. Right, so you have a clipping algorithm where you could do that. So for lines with both endpoints outside the window, test the line for the intersection with all of the window boundaries and clip appropriately. However, calculating lines intersection is computationally expensive, and because a scene can contain so many lines, the brute force approach to clipping is much too slow. So just a brute force method will not work. We need to sort of develop an algorithm which would be efficient in trying to clip these vertices. So line clipping, lines exist with viewable volume plane. Part is visible. Find the real world location of exit points. Shortened lines pass through to rasterization, that is to develop the screen. There must be no difference to the final image. Of course, the final image, since I've clipped the edges, it should not distort the shapes because of the window clipping. So how do I find the intercepting point between the line and one of the edges of the window? Here I see the red color line clipping or cutting through the top edge of the window. So here I have got the 2 points. My first point 1 is outside the window, point 2 is within the window. So here I have got point 1 is x1, y1 and point 2 is x2, y2. With these data, I need to actually determine what is x and y. That is, I will have to replace my x1, y1 with x and y, which will define my segment of the line which is displayed. So this is a simple trigonometric calculations that you could do using the relationships of the triangles. I can easily say that A by C is equal to B by D, and or A by B is equal to C by D. This is basically relations of an orthogonal triangle. So with this, I can determine my x prime and y prime as shown here in these equations. So line clipping, similarly handed for other cases, extends easily to a 3D world. I can do it in 3D world, but expensive below for 2D world. So for 2D world, we see that we need to do a 3 floating point subtractions, 2 floating point multiplication, and 1 floating point division. So and this needs to be done for all the 4 edges. So you need to multiply this by 4 to get the total number of computation required for a particular edge. So now you will have millions of edge, and this will create havoc. We need to save ourselves with some options. The following algos, which are given in Hans and Baker, that is somewhere close to page 224 to 235, will define how to clip the thing. Now, the naive approach to clipping lines: for each line segment, for each edge of the viewport, find the intersection point, pick the nearest point. If anything is left, draw it. What do we mean by nearest? How can we optimize this? So, is the main problem. So there we have to see the trivially accept, big optimization, trivially accept and reject. That is, if some lines are within the window, we should just accept it, and the ones which we are sure it is outside, we should reject it. So this will reduce the load of the lines which I need to clip. But how can we quickly determine whether a line segment is entirely inside the viewport, or a portion of it is jutting out from the right end or the left end of the window? So how can we know a line is outside the viewport? The answer: if both endpoints are on the wrong sides of the same edge, can be trivially rejected. That is, if both endpoints are to the left of the left edge, then you can say that this line or this edge is not going to clip through. Like in this case, what you see here, that both the endpoints are to the left of the left edge. Similarly, if I've got both endpoints to the right of the right edge, again, I don't need to sort of remember, or I can easily clip it. And in this case, I have got both the edges within the window. If that I can check for both the edges, I can check with x min, x max, y min, y max, and find out if both the endpoints are within the window. I will say that I should accept this vertex as part of my vertex. Clip lines to viewport. Discard segments of lines outside the viewport. Trivially accept lines with both endpoints inside all edges for the viewport. Trivially reject lines with both endpoints outside the same edge of the viewport. Otherwise, reduce to a trivial case by splitting into 2 segments. So what we will do is that, let us come to the algorithm which I would like to discuss, is the Cohen-Sutherland line clipping algorithm. Now what we do is that we divide the region into like a game of tic-tac-toe, the window being the central square, and I have got my 8 squares which are outside. So totally there are 9 squares. The center is the window, and rest are portions of the outside. So these 9 regions, I will like to code them. Now I know that I'll choose a binary coding. I know that I cannot code with a 3-bit, because for a 3-bit it'll give me an 8-bit number. So which I need to miss out one of the edges. It's possible that I can miss out the 000 edge, but then that will not help. So what we do is that we take 4-bit number to represent every section of the scene. Now what you see is that for a 4-bit I have got 16 possibilities, but here I have got just 9 possibilities. So I have redundancy, and therefore let me use it carefully or more intelligently. What we see is that I have regions like, for instance, I've got top, middle, bottom. So I've got 3 conditions. Now these 3 conditions can easily be represented by a 2-bit binary number. It could be 00, it could be 10, or 11, or 01 to represent the 3-bit. So what we do is that we separate out the left, middle, right, top, middle, up as 2-bit number. So here you see the green bit is remaining in the top line. The green bit remains the same, while I've got the magenta bit, which is 01, representing the left side of the window. 00 represents the central region, which is the columns of the window, and I have got 10 representing on the right edge, outside the right edge of the window. So similarly, now with these 4 points, I'll have a very good code. Now if I have a line, I'll have this code. Now what we are going to do is that we are going to take each vertex, and we are going to tag with this vertex this binary code of belonging. We will tag it and say that this vertex belongs to this region of my window, okay, or this region of my screen. And if it lies within the window, of course, both the endpoints will be 0000. So I've done is that I've split the plane into 9 regions, assigned each of the 4-bit value, the above, below, right and left, assuming the vertex of the line 4-bit values. Now let us do the computation. As I said, if both endpoints show that the code representing that vertex is 4 zeros, that is 0000, we can say that we should trivially accept it. We know that this particular edge lies within the window, and therefore we don't would like to change its status. So what we do is that we send them back. The second case is if V1 and V2 is not equal to 0, trivially reject. That is, if I have got a line, for instance, cutting like this, going through this, or going through this, or going through the same region, right? So in this case, I see that 10 has remained the same, but my second 2-digit keeps failing. Okay. So I have got, so when I do an AND of these if I've got a starting edge and an ending edge, and if I do an AND of the two, I will see that I will always get a non-zero term in the case where the line is outside. So when I say that that V1 and V2 not equal to 0, it trivial. We'll say that the objects are trivially accepted. And once I know which edge is cutting, so cutting, I know that this is the edge which is 10, which is cutting it. Therefore, I will only send it to clip with this edge and say that how to clip the window. Right. So here I have got multiple endpoints, and with these endpoints I have marked the edges of these endpoints which define the vertices of these endpoints. So here I've got these vertices and it marks the endpoints. Right. So, and with this marking, I know that in the first condition that both these endpoints are 0. Therefore, I trivially accept it. Next, I see that this line P11 and P12 lie. If I take an AND between these two codes, I will see that the AND is not 0, and therefore I take the inverse of it. This will tell me that the line is totally outside and I need to reject it. And here again, in this case, the code is, here you see 0101, and therefore this needs to be rejected. So the red ones will be rejected and the center blue one will be totally retained. So you see it has reduced the number of lines by already 3 lines have reduced from a total lines of 6 lines. 3 lines have gone and what remains is another 3 lines. Now these 3 lines, I know that one of these lines needs this P9 and P10 P10 is on 0100, while this is P9 is at 0000. What you see is that it needs to be clipped by a single edge, so you can easily clip it with this edge. While in this case, I know that they fall on either sides, and therefore I need to clip at both the ends of the vertex. In this case, though the vertex is outside, I just can't make a difference between this P3 and P4, and if this vertex remained here, inside here, I could not have made a difference. So therefore, these lines need to be run through brute force method. Now, if I would like to extend the Cohen-Sutherland clipping algorithm to 3D line clipping, I need 27 regions. Please note that I'll have 27 cubes around my window cube. So what I would require is that instead of having a 4-bit number, I'll require a 6-bit number to represent it in the thing. It can be done in 3 dimension also. And similarly, we can work out for triangles. It still work, but must be done for 2 sets of similar triangles, because you have got 3 sides of the edges, and then you have got regions which is between both the edges, that is the above the 3 vertices of the triangle. So this needs to be seen. Assign an autocode to each vertex of the line. If both autocodes equals to 0, trivially accept. Bitwise and vertex outcode together. If the result is not equal to 0, trivially reject it. So this will reduce practically the lines by 50%. Rest of the lines you need to find out which edge is clipping it, and you need to clip it. So if a line cannot be trivially accepted or rejected, subdivide so that one or both segments can be discarded. Pick an edge that the line crosses. How do I do it? I do it with the code. So here I have got one point which is within the window and one outside. I will know which side is it outside. I know if it is outside from the right edge, top edge, bottom edge, and so I'll choose that particular edge to clip it, or the edge equation. Intersect line with the edges. How do I do it? I have one method that has been shown through using trigonometry or ratios of rectangles or triangles that can be done. Discard portions on the wrong side of the edge and assign outcode to the new vertex. It is possible that in one go I will not be able to clip it. I may need to iterate it twice in some conditions. If I'm lucky, I will do it in one condition. Otherwise, it may require that I need to do it for 2 times or 3 times clipping the window. Okay, apply trivially, accept, reject test, repeat if necessary, and you continue doing it. So what you see here is the algorithm here. This is the Cohen-Sutherland algorithm, and this is an image of Sutherland, and he is also one of the first person who sort of made this virtual viewing devices. We don't have a picture of Cohen, so I've put it as a silhouette black image. But this is how Sutherland looks with his most important discovery, which is there. So this algorithm is based on Sutherland. So here we saw how to do it with trigonometry or ratios of sides of a right angled triangle. But here we can see that we can also use a parametric form of the equation. We could also use the implicit form of the equation. The implicit form of the equation, we plug in the point into the edge equation of the top edge, bottom edge, right edge or left edge of the line. You will see that if the solution is positive, negative or 0, you will say if it is within the line or left of the line or the right of the line, and then decide on the thing. That is also possible. We could also do it with a parametric form of equation. Now, parametric form of equation, you see that this is the parametric form of equation, where you have got x is a separated equation, y is a separated equation, which is shown here. So here you need to show that if my edge parameter is t, I need to show that if the point lies within the window, the parameter value should be within 0 and 1. If it is above 1, it is to the right. If it is below 1, it is below 0, it is to the left. So here define the line between P0 and P1. If t is less than 0, define the lines before P0, and P greater than 1, define lines after P1. So this is how you would do these calculations. So define each line parameter forms. Here I've got this line parameter equation, P0 of t to Pn minus 1 of t. So if there are n number of lines, define each edge viewing point parameter in the form of PLT, PRT. This PL is left edge, PR is right edge, PT is the top edge, PB is the bottom edge. So these are my 4 sides. And when using Cohen-Sutherland, perform intersection calculations for appropriate viewpoint, edge, and line. So here I have got the 2 equations. What you see here, this is my line equation, which is shown here, right? And this is the line equation. Similarly, I have got my viewport equation, which is shown here, which is here the left edge. So I equate the intersection between them will be equating the x value and the y value. When I equate both these equations, I get these two lines. I need to solve these 2 equations for T0 and TL, and while solving I can find out say for in function of TL, and if TL is within 0 and 1, we know that the point is within the window, otherwise it is not within the window. So this is the condition. If the intersection is within the viewing port, then TL is within 0 and 1, and T0 is also needs to be between 0 and 1. That is a point within the two vertices of the edge. So having a point which is outside the edge of the line has no meaning, because it's not part of the segment of the line. It is part of the line but not part of the segment of the line. So the truth in advertising, Cohen-Sutherland doesn't exactly do it this way. You don't need to solve it for T naught and TL. You just need to solve it for one of them, and then the other is simple. The outcode test line edge intersections are quite fast, but some line requires multiple interaction. Fundamentally, more efficient algorithms exist, like Sirius Beck uses parametric line to clip against arbitrary polygons, not just rectangles. So you could do clipping with an arbitrary polygon. This is Sirius Back's algorithm. Please look into it. I'm not going to cover it, but you should know it. Or Land-Barsky optimizes this with upright volume, which is there. So the Cohen-Sutherland other lines, the lines that cannot be identified as completely inside or outside the window, may or may not cross the window interior. These lines are processed as follows. Compare the endpoints outside the window to the boundary. Choose any order in which to consider the boundaries, left, right, bottom, top, and determine how much can be discarded. If the remainder of the line is entirely inside or outside the window, retain it or clip it respectively. So, so these are different sections which you can read or see through the PPT. I will now go quickly. These are some examples. I'm skipping through these examples, and I come through. This is the Lang-Barsky line clipping algorithm. This is the Lang-Barsky line clipping algorithm, which you can go through yourself. And I just need to, before I end, I need to just cover up this portion. Please also go through it. The Nicol line clipping algorithm, we'll try to see what is, this is a pretty fast algorithm, and we will see its difference. It also partitions this space into different sections. In the earlier cases, I had taken the edges, extended the edges of the window to partition the window, but here we will do it differently. Here one of the endpoints of the line will be part of the edge of the lines, which you will use for clipping. So this test is most complicated, also the fastest, only works well for 2D. So please, this cannot work for 3D. So it works for 2D. And quick overview is that by creating more regions around the clip window, the Nicol or NLN algorithm avoids multiple clipping or of an individual line segment as Cohen-Sutherland method. Now, what I'm going to do is that here, supposing my point here, P1, is my first point of my edge, that is vertex. I use the first point as one of the points which actually determine the different sections. So here I've got the first figure, that is figure 611. This figure also exists in the Hans and Baker's book. So what you see here is that I take the point P1 and connect it to the four corners of the windows. This forms the boundaries of my regions of consideration. Now, if how will I know? And I will then consider in the other case it was like a tic-tac-toe. Here now it's a basically a widening triangle or a cone which represents the side. So here I have got, you see that, and how do I determine it? I'll determine it by taking the slope of the line. I'll take the slope if the point P2 is in one of these sides. I will just consider P1 slope of P1 P2 and compare it with the slope and accordingly identify it to a particular side of the window. Okay, but please note that if the point is within the window, it is different, and if the point is in the middle of the left edge, it is different. If the point is lying somewhere near the corner of the window, it is different. Again, we'll have to see it can lie above the diagonal of the window or below the diagonal of the window. This will give me two different conditions. Here I've shown the center portion remains the same, that is figure 11, but figure 612, I've got my P1 is outside on the left side. So by symmetry, I can say that similar partitioning will exist for the top side and the bottom side and the right side. Because by symmetry, these will remain all the same. Similarly, I'll have for all other conditions given. So this is what I would like you to derive or find out the Nicol-Lee-Nicoll algorithm. How are you going to partition this algorithm? What will be the conditions? Here you see the conditions are basically calculating the slope, which is going to give you the Nicol-Lee case, which is here, which I have defined. So Nicol-Lee-Nicoll line clipping algorithm, symmetry handles for other cases, that is we have taken specifically 3 type cases, or we can say 4 type cases. So what we need to do is that using symmetry, the same relationship can be moved for other. Find the slope of the line and the 4 region boundaries of the lines. Find in which region P2 is in. If not in any labeled, the line is discarded. If it is not within any label, so you just discard the line. Subtraction, multiplies and divisions can be carefully be used to a minimum or not used in the process. A note on redundancy. Why represent the multiple forms of clipping? Why we have seen that there are many more algorithms? Because we have seen sorting algorithms work for different sizes of data. One sorting algorithm is more efficient than the other sorting algorithm. So when we want to deal with three-dimensional cube, then we will go into Cohen-Sutherland, or if we are working in 2D, we will certainly look for the Nicol-Lee-Nicoll algorithm. The fastest and the general case isn't always the fastest, and every specialist case. Most sorted list, that is bubble sort. Similarly, here the Nicol-Lee-Nicoll is the most sorted list. History repeats itself. How may you may need something similar in different areas. Grab one that maps best.